This video is the second in a series of applications in linear algebra, and this application will focus on chemistry, balancing chemical equations. The key idea in this section is that to balance a chemical equation, the total number of atoms of each type on the left side of the reaction must match the corresponding numbers of atoms on the right side of the reaction, because atoms are neither destroyed nor created in the reaction. So what we're trying to do is just balance the number of atoms of each type. Here's our problem. Alka-Seltzer contains sodium bicarbonate, or NaHCO3, and citric acid, H3C6H5O7. When a tablet is dissolved in water, the following reaction produces sodium citrate, water, and carbon dioxide gas. So our reaction is NaHCO3 plus H3C6H5O7 reacts, so I have the arrow, to become Na3C6H5O7 plus H2O plus CO2. We are asked to balance the chemical equation using the vector equation approach. So when you're doing these problems, make sure that you're using linear algebra to solve in order to earn credit on your case study. Okay, so what I'm going to do is I'm going to put my unknown coefficient in front of each compound. So I have x1 times the NaHCO3 plus x2 times the H3C6H5O7, x3 in front of the Na3C6H5O7, x4 in front of the water, H2O, and x5 in front of CO2. So those are just my unknown number of compounds of each type that I need, so the coefficients. What I'm going to do to make an equation so I can use linear algebra is I'm going to focus on each atom. So sodium, or Na, hydrogen, H, carbon, C, and oxygen, O. So I'm going to look at this first one, x1 times NaHCO3. So I'm going to have x1, and then I'm going to make a vector, and I look at the compound, and I have one sodium, so I'm going to put a 1 in my vector. I have one hydrogen, so I'll put a 1 in my vector. I have one carbon, so I put a 1, and I have 3 oxygen, so I'm going to put a 3 in my vector. Let's look at the next one. So H2, I have 0 sodiums because there's no Na in there. For hydrogen, I have H3 and H5. So I have a total of 8 hydrogen. So I'm going to put an 8 in my vector for hydrogen. I have 6 carbons, so I put a 6 in the vector, and then 7 oxygens. So I put a 7 in the 4th entry of the vector. Now the reaction is going to be like my equals sign. So I have the equals sign, and then I'm going to do the same thing for the right side of the equation. So x3, I have 3 sodium, 5 hydrogen, 6 carbon, and 7 oxygen, plus H4 times the vector with 0 sodium, 2 hydrogen, 0 carbon, and 1 oxygen, and x5, and I times the vector with 0 sodium, 0 hydrogen, 1 carbon, and 2 oxygen. So there's my vector equation. So now what I want to do is solve this using the methods that we've been practicing. So right now I can't do anything to solve it because I have variables on both sides of the equals sign. So I want to get everything to one side of the equals sign. So to solve for x1, x2, x3, x4, and x5, change the above into a homogeneous vector equation and solve. So homogeneous, remember, means it equals 0. Every equation equals 0. So I'm going to take the vector equation that I found before, and I'm going to move the x3 vector, the x4 vector, and the x5 vector to the left side of the equal sign, and I do that by subtracting. So to move it over, just like I would with a regular equation, if it's added on the right side, I subtract it on the left. So I end up with x1 times the x1 vector plus x2 times the x2 vector minus x3 times its vector minus x4 times its vector minus x5 times its vector. And then all of that equals the 0 vector. So I moved the right side over by subtracting. Okay, now this still is not in a form where I would just plug it into an augmented matrix. I actually want the signs, those negative signs, to be on the coefficients. So inside of each vector. So I'm going to rewrite the equation with appropriate signs on the coefficients. So in other words, I should have an x1 plus an x2 plus an x3 plus an x4 plus an x5, and then the vectors will incorporate the appropriate positives or negatives. So I have x1 times the vector 1, 1, 1, 3 plus x2 times the vector 0, 8, 6, 7 plus x3 times the vector -3, -5, -6, -7 plus x4 times the vector 0, -2, 0, -1 plus x5 times the vector 0, 0, -1, -2. And then it all equals the 0 vector. Now you're ready to solve. So stick it in an augmented matrix and row reduce to solve. Okay, so here's my augmented matrix. It just has all of the coefficients I read off to you from that vector equation. If I row reduce, I end up with the matrix, the augmented matrix, 1, 0, 0, 0, -1, 0, 0, 1, 0, 0, -1/3, 0, 0, 0, 1, 0, -1/3, 0, and 0, 0, 0, 1, -1, 0. Now remember, in an augmented matrix, each column represents coefficients for a certain variable. So I have my x1 through x5 variables. And so when I translate this matrix back to equations, the top row gives me x1 minus x5 equals 0. The second row gives me x2 minus 1/3 x5 equals 0. The third row gives x3 minus 1/3 x5 equals 0. And the fourth row gives x4 minus x5 equals 0. And because there's no pivot in the x5 column, x5 is free. Okay, so now I translate that set of equations into my solution. So moving all of the free variable terms to the right side of the equation, I get x1 equals x5, x2 equals 1/3 x5, x3 equals 1/3 x5, x4 equals x5, and x5 is free. So now here's a key idea when you're balancing chemical equations. Since the coefficients in a chemical equation must be positive whole numbers, in other words, you cannot split atoms, so you cannot have parts of each compound. So you have to have positive whole numbers as the coefficients. So we pick the smallest value for the free variable that will make every xi a positive whole number. So if you look at our solution, we have a 1/3 x5 and a 1/3 x5. If I let x5 equal 3, then x2 and x3 will come out as whole number coefficients. So you use the lowest common denominator of the coefficients on the free variable. So in other words, if I had instead, let's say I had a 1/3 and a 1/2, then I would let x5 be 6. So whatever your LCD is, you let your free variable equal that number. Okay, in this case, x5 equals 3 is going to give us all whole numbers. So I put in x5 equals 3, and I'm going to get 3, 1, 1, 3, 3. So those are my coefficients. And our goal was to balance this chemical equation, the Alka-Seltzer dissolving. Okay, so if I put in the appropriate coefficients, I'm going to get 3 NaHCO3 plus 1 H3C6H5O7 reacts and gives 1 Na3C6H5O7 plus 3 water plus 3 carbon dioxide. And that's going to be your balanced chemical reaction.